Hello, everyone. So today we're going to be trying to bring a lot of the ideas that we've been building up over the last couple weeks together by looking at how we can determine the orbital energies for a diatomic system. So specifically, we're going to be dealing with the much tougher case of a heteronuclear system by playing around with some acid. So today we're up to hydrofluoric acid. So the starting procedure when we're dealing with a heteronuclear species is we're going to have to use a much fuller form of our orbital energy equation. Now, because I'm not completely made out of time and it gets really messy, we're going to be making the zero overlap approximation, which provides the relatively simpler equation form that we derived above. Please, if you want to have a refresher of how we did this, return back to the video on orbital energies. So what we're going to be making use of is the knowledge we gained last time, looking at how we can determine the uh, atomic orbital energies, or the Coulombic integrals, for two different atoms, so A and B, combining that together with a little bit of information about our resonance integral, and we can use this to determine our bonding and our anti-bonding energies. So in order to start with this, we're going to need our two Coulombic integrals. So a good place to start is to make use of the ionization energy and electron affinity tables in the back of your book. So I went ahead and made use of this to grab the energies for hydrogen and fluorine. That way we can make some hydrofluoric acid. So the values are provided down here. But one of the things I do want to kind of point out is that if we compare the individual values for ionization energy, electron affinity, and a Coulombic integral for these two cases, you're going to find that hydrogen is much more readily able to lose an electron than fluorine, much less likely to want to gain an electron than fluorine, and this results in a much higher atomic orbital energy by over 3 eV. And another way of thinking about this is the fact that it is much less electronegative. So again, this is something to be thinking about when we're talking about electronegativity. The larger the larger the electronegativity, the lower down the orbitals are. And it will turn out that the difference in between our atomic orbital energies do play a fairly significant role in bond character. So thus hydrofluoric acid, with its big difference in orbital energies, is a quite illustrative example. So we can take this along with our particular energy equation and use it to determine our two MO energies. So one of the things I want to make note is that this leaves us with one last variable we do not know, and that's our overlap, or our resonance integral, which you actually have to do a little bit more math to determine. And typically you are going to need to know the distance between the two atoms to help inform this value. So we're going to take a fairly typical resonance integral value of about -1 eV. And again, don't forget, we already made the zero overlap approximation, so we're assuming relatively low overlap between the atomic orbitals. Now, as we've seen previously, this is not the best approximation, but it does give us a fairly easy way to build up the equation so we can kind of intuit what's happening a little bit more easily without having to go through a lot of the rigorous derivations of S values that we had to do previously when we were looking at simpler systems. So what we can then do is taking these four values, plug them into our previous equation, and we get a nice expression for orbital energies. And again, this is mostly monitored, controlled by the average of our two orbital energies, and then the uh, the stabilization and destabilization of bonding is largely driven by a combination of our resonance integral and the difference in between our two and energies between our two atomic systems. And so when we put this together, we find that the energies for our molecular orbitals are going to be centered around a value of about -8.8 eV. with the with the bonding orbital stabilized by about 1.9 eV and the anti-bonding orbital destabilized by 1.9 eV as well. So putting this together, we can generate a bonding orbital energy of about negative 10.7 eV and anti-bonding of about negative 6.9. Now, what you may notice is that this ends up yielding a difference of almost 4 eV in between our bonding and anti-bonding orbitals. So this is a fairly significant energy difference between our two molecular orbitals. But this is a point where I want to actually illustrate something that's fairly important, which is the idea that while this difference seems fairly large, if you compare it to our original starting atomic orbitals, you're going to find most of that difference was actually driven by our two starting atomic orbitals, which were already over 3 eV separate. And what you'll find is that the bonding orbital is only stabilized by 0.3 eV below the fluorine atomic orbital. While similarly, the antibonding orbital has been destabilized by about 0.3 eV over the hydrogen orbital. So again, what we're finding is a very significant link in between bonding orbital energies and our original starting atomic orbital energies. So MO energies and atomic orbital energies can be very tightly related. And while it might not be quite so obvious from our original starting equation, we can make a couple of approximations that will illustrate this important relationship. So we can go ahead and start with our zero overlap approximation. And then let's go ahead and think about an important idea. Let's focus on this limiting case of what happens if my atomic orbitals are very different in energies, or if you think about it in terms of electronegativities, they have very different electronegativities. And this can be a little bit more of an intuitive way of thinking about it. So if that happens, this denominator is fairly large, the numerator is fairly small, and this gives me a relatively small x value. And using that, we can use some mathematical tricks that we used a little bit last semester, but I won't go into too much detail here, which lets us simplify everything in terms of the square root, after which we can go ahead and annihilate a couple of these terms to give two very simplified expressions. And this is the idea that my antibonding orbital, and yes, I did shift notations, is going to start at my higher energy atomic orbital plus a raw magnitude of my resonance integral. So this is essentially telling me about how well they interact. Plus, again, the positive difference in between my two atomic orbitals, where we are, for the sake of signs, going to represent B as the atomic species that possesses the lower atomic energy. So this is going to be a more negative value, generating a positive value in the denominator. So I'm going to have a negative number plus a destabilizing correction. But the important thing to kind of note here is that what we find is the antibonding orbital is going to be relatively similar to the original starting higher energy atomic orbital, in this case, hydrogen. And the larger the difference in between my two atomic orbitals, the more similar my antibonding and my atomic orbital energies get. So again, this helps illustrate an idea we've occasionally seen in Gen Chem. The more different two elements are, the more the orbitals of the bond look exactly like the orbitals of the atomic species. One might even call this that they'll start looking more like an ionic case, because at that point, my atomic orbitals are the exact same thing as my molecular orbitals, and the electrons simply fill the lowest atomic orbitals, and there's no actual orbital mixing. So this is an actually fairly useful thing to think about. And the same thing will hold for the bonding orbital. And really, the important part is it's just illustrating that as the gap in between my two atomic orbitals widens, as the electronegativities differ by increasing amounts, that my bonding orbital looks a lot more like A, and my antibonding orbital looks a lot more like A, and my bonding orbital looks a lot more like B. So again, if we have a big separation, MOs and AOs don't actually look that much different. And we can look at this a little bit more numerically if we go back to the case of hydrofluoric acid. So when we have our hydrofluoric uh, acid, and we can take the four energies we derived, both for the atomic orbitals and for my bonding and anti-bonding orbitals. So what you'll notice here is that my uh, hydrogen orbital is actually fairly close to my anti-bonding, and my uh, bonding orbital is fairly close to the lower energy fluorine. And that essentially I take my two atomic orbitals, and then using the resonance integral and the difference in between the two orbitals, I'll push my two MOs equally up and down from the starting. And again, our energies are all set with regards to this whole ionization limit to have a standard reference value. So again, our fluorine atomic orbital is going to greatly resemble our bonding MO, and our higher energy hydrogen atomic orbital is going to look a lot more like the anti-bonding MO. Now, we did this all through energy arguments. What we need to do is actually see what the orbitals themselves look like. And for that, I need my I need my coefficients that tell me exactly how much of the hydrogen character and the fluorine character are in each of my bonding and anti-bonding MOs. And we will go ahead and derive that next time. Till then, take care and stay healthy.